interested in measuring species concentrations or temperature, velocity, some parameters in a quantitative way. So it's not the quantitative calculation of the spectrum I'm talking about, it's the application of the laser diagnostics to measure things we care about in combustion in a quantitative way. And that's why I'm so interested in absorption and fluorescence as the two techniques that lend themselves to quantitative measurements, especially absorption. So that's the origin of the title. Now, it's line positions, line strengths, and line shapes. How do we go about characterizing the strength of lines? It's like the probability that if you're in a quantum state and you're exposed to radiation of the right wavelength that corresponds to an allowed transition, what's the probability per second that you'll absorb that photon? That's the fundamental quantity. Or you're in an excited state and you have an allowed transition available to you, or maybe more than one, and in the absence of any collisions, what's the probability per second that you will spontaneously emit and go to that state? And you have to rely on probabilities because we're dealing with microscopic systems that don't lend themselves to exact answers. So if you're in an excited state, on average it might be 100 times a second that you would radiate, or 1/100th of a second is the average time you'd stay there. But that's just an average. It will be a distribution. So with microscopic systems, we have to deal with that. So we want to introduce now, today, in this hour, how we think about this in a fundamental way. And this will develop the equation of radiative transfer in Beer's law, which is the fundamental law for the absorption of monochromatic light. To get there, we have to introduce what's known as the Einstein theory of radiation and the Einstein coefficients. And they're the fundamental parameters that we talk about. They're numbers representing a fundamental process, but they can either be measured or calculated depending on the situation. Okay, and this will lead us to what we call the spectral absorption coefficient, and radiative lifetime, and some line strength. So I use the word strengths kind of broadly. They're really, these strengths are are probabilities of some process. And they're to be related back to these even more fundamental properties known as the Einstein coefficients. So we're going to do kind of energy balance. And we're going to imagine we have a collimated laser beam at a frequency nu and an intensity I sub nu, where that might be watts at frequency nu, or watts in the vicinity of nu, or watts per unit frequency, or watts per square centimeter. There's a lot of different interpretations of this intensity. But imagine that it goes through a sample of gas, an emitting, absorbing gas, and comes out with some modified intensity. Why? Well, if it's absorbing, then it's going to come out with less. If it's emitting, it might come out with more. So we're going to try to do an energy balance, and we're going to gradually work our way towards using this to define our spectral absorption coefficient, and then relating that to the Einstein coefficient. So the sum of all the possibilities are it's either going to absorb, reflect, scatter, or transmit. And we're mostly talking about situations which don't have scattering and they don't have reflection. So we can kind of idealize this a little bit and say, let's assume that situation. And we assume it's a clean situation, and we get some relationships. Those relationships still hold if it's not a clean situation. Frequently you do this in chemical kinetics and a lot of situations where you imagine the ideal situation where you can develop some relationships, like the rate coefficients in a reaction. They're always related, regardless of whether you're in equilibrium or not. The rate coefficients are related because they are fixed by their relationship at equilibrium. So at equilibrium, they have a relationship. You go away from equilibrium, the rate coefficients don't care whether you have equilibrium or not. They drive the process. Same thing here. So we're going to just think about absorption and transmission right now. So let's imagine the situation where the sum of the absorption and the transmission must be 1. We're going to define the absorptivity then as a fractional change in I per unit length. That's di over I. And we say, well, and it's also proportional to the length. So let's introduce the spectral absorption coefficient and call it K sub nu. That says if you're at frequency nu and you undergo this this negative change from here to here. That spectral absorption coefficient is just a number per unit length times the length. The quantity together is called the absorptivity. It doesn't have, it has no units. Now, this is then just the fractional change in the K then is the spectral absorption coefficient, is the fractional change per unit length. And again, it may have different units. That's not a problem, that's not an issue. Sometimes it's specifically at frequency nu, or it's in a narrow range between nu to nu plus d nu. But this is now this is per unit length. So K sub nu is per unit length, 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ frequency, I nu over d nu. There's a lot of different ways we can do this, but right now I'm doing this at a frequency nu. Now that we're working towards doing an energy balance. So here's our di nu, and you know that there's something called the spectral emissivity, that is the relative value of the emission at nu divided by the black body emission at nu. So this is a thin slab, everything's uniform inside. The emissivity is the ratio of the emission at nu. This would be the emissivity at nu. Would be the ratio of the emissivity of the emission to the black body level of emission. So hopefully you're familiar with that. And then hopefully you've heard of Kirchhoff's law that says emissivity equals absorptivity. Where'd that come from? At equilibrium. You go to equilibrium where everything's in equilibrium and you find certain relationships. Then when you go away from equilibrium, they still hold. So it's a general rule that the emissivity equals the absorptivity. But we just did the absorptivity. And now this is the emissivity. So we have both the emission and the absorption. And if we put those things together to evaluate di as the difference between the emission and the absorption, we derive this simple relationship here, important enough I put it in a red box. And it's known as the differential form of the equation of radiative transfer. And it says that the incremental increment in intensity at frequency nu is proportional to the difference between the black body emission and the local intensity and the spectral absorption coefficient. So all of a sudden, I don't have any more emissivity absorptivity. I've got this relationship in terms of K. So here's my relationship again. This is the di nu is proportional to the difference. So I can also integrate this over length, and let's assume that it's uniform over that distance. So now I can integrate this and have what's called the integrated form of the equation of radiative transfer. And so this is just the integral of this equation, where I nu 0 would be the incident intensity, and that's the black body intensity. And we see this quantity K nu L everywhere. What's K? The spectral absorptivity. I'm not telling you where we get it yet. It's just, it is what it is. But this quantity together, K nu L, is called the optical depth. That's the definition, or the common terminology. So right away, this is the most general form. It's at frequency nu. It's not integrated yet. And it's easiest to think about when you have, say, collimated light. So if we have collimated light with incident light, that means I nu 0 is typically a big number. And that just means that's the term we're going to use when I nu 0 is big. If there's no incident light, we only have this term. We only have emission. So, but this equation lets us examine both cases, and you can see how it depends upon optical depth. If K nu L is big, optically thick, none of that light gets out. But what gets out is the black body emission. If K nu L is small, then it's called optically thin. So the two limits are optically thin and optically thick. So there's two especially interesting cases, emission and absorption. We look at our equation here, and we take the case where it's emission. That means we have no significant incident light. We're just worried about the emission. And now we can evaluate, we can call this the spectral radiancy, and we can also evaluate the spectral emissivity then to be the ratio of the emission to the black body emission. Well, that's interesting. So now the emissivity has a simple interpretation in terms of the optical depth. If I tell you K, nu, and L, you could kind of right away tell me quite a bit about this problem. You can also integrate over nu. We haven't said anything about an absorption line here. Just there's some sort of absorption going on, or maybe there's not. K nu might be 0. But we can integrate over frequency, and why do we do that? Because when you integrate the black body emission over frequency, what do you get? You get sigma t to the 4th. So this now becomes an expression of the emissivity at frequency nu, or path length L, because it depends on L. Depends on L. If there's, this is the emission case, so if L is 0, there's no emission. If L is infinity, then you get this term here goes away and you recover. What would you get for the emissivity in the limit of infinite KL? It's optically thick. This term goes to 1, and I get the integral of IVB over d nu, which is sigma t to the 4th, and the emissivity becomes 1. Optically thick, emissivity is 1. Optically thin, emissivity goes to 0. So the emissivity, property of gases at frequency nu, depends upon the absorption coefficient. So if we're between lines, there's no absorption, then there's no emission. If you're on an absorption line, then there's also emission. So you can have different amounts. You can have single lines, multiple lines, continuum. You can have all sorts of radiation to come into play here. Key thing is we've now got an equation of radiative transfer. We can deal with emission or absorption at frequency nu. When you integrate over nu, you have to decide now what is K sub nu. It's different for CO2 than for H2O and so on. But K nu L is what counts. It's either optically thick, optically thin, or somewhere in between. Optically thin is kind of a nice case because K nu L being small, you can expand this term and you just get right here, all of this, you just get K nu L. Absorption. This is the one that we like a lot. This is the one we use for laser absorption experiments. So now we go back to our integrated equation of radiative transfer. We drop out the emission term. Why? Because our source is bright. We've got a laser, it's bright, much brighter, higher temperature than our absorbing medium. So now we now look at the reduced form of this equation is in fact Beer's law. Transmitted intensity is the incident intensity times e to the minus of the absorbance, or K nu L. This is known generally as the Beer-Lambert law. Sometimes it has other names, but it depends a little bit on the units that are used. But I call it Beer's law. So the fractional transmission is given by this exponential decay law. Why is it exponential decay? Because K nu is the absorption coefficient per unit length. The absorptivity grows linearly with the length. Therefore, it's an exponential process. Now, you can use this, right now you can imagine this is kind of a steady problem. Intensity is constant going in, and you can measure what comes out. But in fact, the same equation applies if you want to have a pulse of light, send in a blob of photons, what fraction come out. It doesn't make any difference whether it's the number of photons per unit time, the number of photons in a pulse. The same relationship holds, but it's only for monochromatic light. This is a kind of an important point. So it only holds for monochromatic, or effectively monochromatic light. If you have a broadband source and you send it through a gas, and some of that light is at a wavelength that's not absorbed, that light's coming out, and Beer's law doesn't hold. So that's a very important distinction. Okay, now we want to move towards saying, well, that's great. K nu is great. How do I get it? What is it? What's it due to? And the way it's explained is in terms of the Einstein theory of radiation. Now we're starting to get into statistics. So we take the simple case of an atom or molecule that has two energy states that are optically connected, allowed transitions. I could have written a large number. It's enough to look at 2. Lower state 1, upper state 2. And we have molecules that might be in the upper state or the lower state. So if you're up here, you may undergo, and this is an allowed transition. It's an allowed transition. You may spontaneously emit with this probability per second of A. So the probability per second that a molecule here, a molecule there, will emit and go to here. Some number. 10 to the 3, 10 to the 5, 10 to the 8th, probability that that process will take place. In parallel, there are two induced processes. So if you're sitting here and you're exposed to radiation at the proper frequency, nu, you can go from here to here. And your probability per molecule per second of a molecule sitting here doing this is the product of two terms, B12, I think that's B12, B12 times rho of nu. B12 is the fundamental number, which is, and rho in this initial form of the Einstein theory called the Milne theory. Rho has units of photon density. It's like photons per unit volume. It's kind of a crazy unit. We're going to get rid of it soon. It just says that if you increase the photon density, you double the photon density, you double the chance of this happening. So this is the probability per unit spectral density that a molecule here will go here per second. But for that process to occur, you also have to allow this one to occur, the inverse. So now we call that B21. So you can go from here to here, or you can go from here to here. So energy's up. Now on this diagram, what have I left off? I've left off collisional processes. That's okay. You can examine a case that has no collisions to get certain relationships, and then you can still use them in a case that has collisions. Well, the Einstein coefficients will be unfamiliar to many of you. It's the probability that a molecule, B12, probability of a molecule in state 1 exposed to radiation of spectral density rho, which will have its units, will absorb a quantum and go to 2. Probability per second, per molecule, and so on. A is the spontaneous probability. These B's are the induced probabilities. So imagine a situation where there's very few collisions. These are the only things happening. Now you can imagine what's the situation at equilibrium. What are the relationships we can get by examining equilibrium? So we know that at equilibrium, all microscopic processes are balanced. And so we can do what's called detailed balance. We can write a rate equation for the population in 2. That would be the number of molecules in 2. Right now we're not worrying about whether it's per unit volume. It's just a number in 2, and that dotted means time derivative. So the rate of change of the population in 2 is a result of the ones that promote the population and the ones that deplete the population. There's only 3 possibilities. This is the time rate of change. What's the time rate of change at equilibrium? 0. So you go to 0 to find certain useful relationships. So you can find this relationship. You can solve for N2 over N1 from this relationship. What else do you know about N2 over N1? You know from statistical mechanics how it's related to temperature. You also know then that it's G2 over G1 e to the minus H2 over KT. You don't need a partition function because you're taking the ratio of 2 populations. So now I have 2 relationships that must be equal at equilibrium. And then you can ask whether or not they break down away from equilibrium. I can use those to solve for rho. That's the spectral density, if I wish, because I have one equation here to solve. You also know, if you've read about Planck's blackbody radiation, this relationship. And those things must be equal. So you look at those equalities and you can draw some conclusions. You can show that, therefore, G1 B12 equals G2 B21. What are the G's? The degeneracies in the 2 states, 2 levels. What are the B's? One's the probability for going up and one's the probability of coming down. If the G's are equal, the B's are equal. You also can find the relationship between A and B. A21, I like this one because it has simple units. A has units of seconds to the minus 1. Otherwise you get really hung up on the units. Sometimes you get hung up on the units. The inverse of A is sometimes called the radiative lifetime. So if you take the average, A is the inverse of the average time. So if A is 10 to the 5th, this is 10 to the minus 5th seconds. So see what we got? Einstein theory has immediately told, without worrying about collisions, there's no collisions in this problem. We don't need it. I immediately have relationships between A and B and the G's. And they will not be affected by going away from equilibrium because they had to hold at equilibrium. So you examine them there and to draw the conclusions you're entitled to, and then you go away from equilibrium, and most of those relations still hold. Okay, now I'd like to get rid of this rho, which is a nasty thing. They developed that back way before the laser. So if you relate this to a collimated laser beam of intensity I, you can show that where the units of I are in watts per square centimeter per unit frequency. Watts per square centimeter per unit frequency. In that system of units, then rho is I over C. This is monochromatic right now. What's the link to K? What I want to do is replace K with a fundamental quantity. I haven't told you yet how we're going to get the fundamental quantity, but it's fundamental, it's lasting, it's there. It's different for every transition, it's different for every species, but it's a fundamental number. Okay, so the simple entry-level theory of Milne was to say, well, I got to be realistic. There is some sort of an absorption line. I don't know what it is, so I'm going to imagine that it's a little rectangular region. This is the transmitted intensity. There's my absorption line. I want to see if the absorption line width makes any difference. So from Beer's law, we had this transmission is e to the minus k nu L. So the transmission is either 1 or it's suppressed by this amount right here. This would be the k nu right here. So what I do is I do a kind of an energy level or power match, and we talk about the absorbed power, and it depends upon the amount of incident power per unit. This is now watts per square centimeter per unit frequency times the frequency width. So that's going to be watts per square centimeter attenuated by k nu L. In the thin limit, just for convenience, you can see that therefore the absorbed power is proportional to the amount you send in. I0 delta nu is how much power I'm sending in, and that's the absorptivity right there. Now we got to relate this to the Einstein coefficient. So we go back to our little diagram again, and we look at, and we write now the induced emission. Now I'm doing this when lowercase n, I'm talking about number per unit volume. Could have done this total number, but I'm going to do it number per unit volume because I want to get back to a power match. So this induced emission is the molecules per cubic centimeter in state 2 times this probability in the original units times the energy per photon. So I've got to multiply, this is basically the number of photons. Now I've got to multiply by the energy per photon. Then I can look at the induced absorption, do the same thing, and I can substitute my relationship that keeps things simpler in terms of intensities, and I work through some algebra and I derive this equation. And what's the significance of this equation? It gives me the absorption coefficient per unit length as a function of one of the Einstein coefficients, the number of molecules in the absorbing state. This term is called the induced emission term. In many cases, h nu over kt is such a big number that it's practically not there, but it's called the induced emission term. All this says is that the absorption per unit length scales with the probability that the photon of the right energy will cause the effect, times the number of molecules there you have, times some constants, and 1 over delta nu. So the line width does make a difference. Why? Because that really is the amount of radiation that's going in. So the line, that just tells me that the line width makes a difference. So K is proportional to B and the number of absorbers and 1 over the line width. So if I make that line narrow, the absorption coefficient gets bigger. That's telling me that it does depend upon the shape, and we better go back and be more careful with a more realistic line shape. So now we recognize the line shapes look something like this. These happen to be the water vapor absorption spectrum in some vicinity. Looks like it's around 6,000 wave number, so say 1.5 microns. Doesn't really make any difference. So what we're doing now, what we're going to do next, we're going to try to keep working on the spectral absorption coefficient, but recognizing we need to use a better model for the line shape. And we'll introduce the radiative lifetime, and then finally we'll talk about line strengths. So now we'll go back to our original equation. That's the integrated form of the equation of radiative transfer. We're going to apply it to, here's what we did before. We had a boxcar line width. This was our result. Now we're going to go to a realistic line shape. And let's see. Here we are. We're going to replace this with this. We don't yet know what the shape is. We just know that this is not realistic. Let's assume that it has to go to 0 in the wings. If you get away from the line, there's no absorption. So it has some sort of an arbitrary shape, not yet defined, but we don't trust that one. So if I convert that, remember from transmission, I can solve for k nu if you tell me length, L. This is k nu. If this is the absorption that we see, this would be the absorbance or the spectral absorptivity we see here. And now what we do is we recognize it has some kind of a shape. We usually characterize the half width, the width at half the height of K. It's not the width at half the peak absorption. It's the width at half the peak of the absorbance because of the exponential. And that's usually called the full width at half maximum, delta nu. I still don't know what the shape is. I'm trying to be realistic. So now we go back, and here's our Beer's law then, and we recognize that this shape function, we're going to define a shape function that is k over the integral. This means that the integral of this shape function is 1. So we've defined a function. We don't yet know what it is, but we're forcing the area to be 1. Now, remember before we could look at the integral of k nu d nu and think previously it's kind of like the maximum value and the half width. It's kind of an area. And so you can see already that this phi is kind of like 1 over delta nu. So I can anticipate the answer already. My spectral absorption coefficient equation, instead of being 1 over delta nu, is going to be just phi. I can already see it coming because we had this 1 over delta nu before. So we go back to this plot, and we recognize now that instead of having, we now have to look at very select frequency intervals, nu to nu plus d nu. So instead of just doing this arbitrarily at treating it the same across the line, we have to recognize that these probabilities depend upon the shape. Whatever it is, it's phi of nu d nu. You go back through this analysis, exactly the same as before, and we do the same energy balance. Everything is the same, and we get this answer. K nu is h nu over c, and it makes sense. The absorptivity or spectral absorption coefficient is proportional to the number of molecules. The more molecules you have, the more absorption you have per unit length. Depends on the fundamental probability, B12, this induced emission term that is always approximately 1, and the line shape function. Therefore, the line shape function makes a difference. And if I integrate this, if I define as the line strength the integral of k nu d nu, which now has units like this. If I have centimeters to minus 1 for, looks like my pointer's dying. I have units to centimeters to minus 1 here for k, and the units of frequency are seconds to minus 1. This system, this line strength has these units. And if I integrate it out, I get rid of the line shape function. So this now is my most fundamental relationship. That what I'm calling the line strength is proportional to the Einstein B coefficient and the number of absorbers. The strength of absorption is proportional to the number of absorbers in state 1. And a fundamental term B that I'm going to get from somewhere. Now, unfortunately or fortunately, there's a lot of units here. So the line strength has got different units. The way I just did it, it has units of centimeters minus 1 per second. But it's also can be written. I'm going to talk about some different units, but it's also, this is in terms of the A coefficient. It's also sometimes written in terms of what's called the oscillator strength. F12 is called an oscillator strength. And oscillator strength came into being because some people who did classical calculations of an oscillating electron, calculated the probability of emission or absorption for that oscillating electron. And they awarded it a value of 1. And so FEL, or F12, is kind of like, well, how big is what's our probability relative to what an electron would have? Free electron. So that's why this came about. F12, sometimes called FEL, is like a probability compared to probability relative to that of a free electron. You got two batteries for me? Good. Oh, great. No, it's this one. This is the one. This one's okay.
Here's your car keys.
Yeah. Okay. So there's probably another pointer here. Maybe not. Okay. So I can use the one that's on here. It just isn't as good. I like green. Okay. So you'll see this line strength in different forms. You'll see it in terms of an A coefficient. Now I can see which one I'm going to push here. Let's try this. It could be in terms of the A coefficient, which has nice simple units, seconds to the minus 1. Or it's in terms of this quantity here. I wonder why I'm not getting the red now. What do I do? There it is. Am I blocking it? Okay. Or it can be written this way. Pi e squared over mc. What are the units of that thing? Electrostatic units. Nasty. So I usually tell the students exactly what the value is. So the point is, this fundamental quantity could sometimes be written in, thanks a lot, in different forms. Oscillator strength, A coefficient, and you got to be careful about the units. Why? What are the units of N1? Number per cubic centimeter. Therefore, we got to honor that. Sometimes we're going to write this in terms of a partial pressure and make use of the fact that Pi equals NIKT. Oh, now we've got different units for S. So the line strength units are kind of vary with wavelength region. I like units that are centimeters to the minus 2 per atmosphere. Some people like centimeters minus 1 per molecule per unit. They use different units. So you have to be real careful about the units of line strength. This oscillator strength then is, as I said, is related back to electrons. And this block of units here, there's a comma. This block of units has these units. This block of symbols has these units, 0.0265 centimeter squared hertz. Centimeter squared hertz. So that's because of this electrostatic unit issue that I've solved for you. Now, so you could write it this way. I put in these units for you. So here's the units. Here's the S in terms of this number and the oscillator. Now, what are the units of the oscillator strength, F12? It's unitless. It's a ratio. This thing is usually close to 1. So that just says that this line strength is kind of like a constant times the number density times the oscillator strength. The fundamental number is the oscillator strength. The line strength goes up with the number of absorbers. Now, just to keep things straight, the number density at STP is about 2.7 times 10 to the 19th. Typically, this number is less than 1, so you can kind of don't worry about this term. So that just says that, to a good approximation, this centimeters minus 2 per atmosphere is just a number. So you're going to have to live with the fact that this thing appears in many different forms. What's important? K is what we care about. Why? Because K nu L is the optical depth. What's K? K is S phi. S doesn't care about phi, but the line shape is important. That's why it's line positions, line strengths, line shapes. We got the strength, we got the shape. You need the two together to say what the absorption coefficient is going to be at frequency nu in our system. So anyway, the notes will take you through some examples here of how some numerical values, so I'm not going to spend any time on them now. You can look under, almost always h nu over kt is much greater than 1, so you can kind of simplify this thing down. I like, this is a nice one here because you can, A has always got some simple units, seconds minus 1. This number is always kind of like 1. That just says that the line strength is proportional to the number density. If you want to do this at a given, if you want to ratio this, F over A is just a number and a wavelength squared. So if you know A, you can get F. If you know F, you can get A. You just need to know the wavelength. So there's a lot of simple relationships that are in the reader, in my notes. Okay, I think I'm going to do some examples. This is a question of resonance transition. What's a resonance transition? A resonance transition is the one that links the ground state of an atom to its first excited state. That's called the resonance transition. It's a strong one. Those are typically very strong. We've been talking about molecules, but when you talk about atoms, electronic transition, an atom can only have electronic transitions. There's no rotation, no vibration. When you talk about a molecule or an atom like sodium, which is the first column of the periodic table, alkali metal it's called, this is some notation again. This is how, this is a particular spectroscopic transition. And the rule of thumb for atoms is that you put the quantum state, the lower quantum state on the left and the upper quantum state on the right. The rule for molecules is reversed, unfortunately. So this tells me, this is the term symbol that tells me everything I need to know about the lower quantum state. That happens to be the ground state of sodium and the upper state. That symbolism has a lot of information in there. In particular, it has this ratio that happens at about 590 nanometers. So the convention for atoms is you put the lower on the left and the upper on the right. The convention for the molecules is reversed, and we usually use an arrow which tells you whether you're looking at emission or absorption. So here's our expression again, this F. So what's tau? Tau is 1 over A. So F tau is this number, and at this wavelength, it's just a number. And the measured tau, what is tau? If the atom is in the excited state and it's left alone, what's the average length of time before it emits? Turns out to be 16 nanoseconds. You can measure that. So if you measure that, you've just determined A. You've just determined everything. So you can, how do you get these fundamental parameters? The easiest one to do is to measure A. You create a situation in which a molecule or atom is allowed to emit in the absence of collisions, and you watch how long it is on average. That's A. Or gives you this tau, and A is 1 over tau. That's one way to do it. Or, since I just showed you that Beer's law is related to the fundamental A and B, I could measure the absorption in the path length and solve for A. So you can get this information in a variety of different ways. Usually it's measured more accurately than it can be calculated. If I take this atom, which is a alkali metal, it's the closest you get to a pure electron. So it's not a surprise that when I solve for the oscillator strength, I get 0.3. If you do this for molecules, you get numbers like 10 to the minus 2, 10 to the minus 4, 10 to the minus 5. Molecules are well removed from a free electron oscillating up and down. But because sodium has only 1 electron in the outer orbit, so it's the closest you can get to a free electron. Therefore, the oscillator strength, which is unitless, it's the ratio to free electron, is 0.3. So typical oscillator strength. So these are the transitions for sodium. And these are different transitions. They have different oscillator strengths. Now I go to a molecule like CO. Now what's happening? This is a rho vibrational transition. This is a fundamental transition. This is the first overtone. So over here, here's the frequencies. Look how small the oscillator strength is. 10 to the minus 5. 10 to the minus 8. So on. So rho vibrational transitions are much weaker, have much lower probabilities than electronic transitions. No surprise, an oscillator strength 1 corresponds to a free electron. And sodium is closer to a free electron. A molecule that's just vibrating is a long ways from a free electron. So if you think in terms of oscillator strength, these look pretty weak. Although the one I like the best is CN. CN, this is now an electronic transition. It has an oscillator strength of 10 to the minus 2. 2%. That's by far the biggest. It's I think about 50 times higher than OH. CN is a pretty strong UV absorber. So what have we done? We've shown that you can go from, we can derive Beer's law, we can derive emissivity. It's in terms of a spectral absorption coefficient K, and we've related that to the product of S and phi. You have to use line shape to be specific at frequency phi, nu. But the integrated line strength is a fundamental quantity that depends only on an Einstein probability and the number of molecules per cc in the absorbing state, N1. Well, what's N1? It's the Boltzmann fraction times the total number of that species. We're going to use the Boltzmann fraction too. So this is the rate equation for radiative decay. So you have to imagine you're in an upper level. Maybe you have the opportunity, maybe you have selection rules that allow you to emit at 3 downward. So you write a rate equation for the rate of decay of this, and you have to sum over the individual Einstein probabilities, AUL. Each transition has its own A. Totally fundamental, doesn't care about line shapes, nothing, it's just a number. And therefore, the average lifetime is 1 over the summation of the A's. So if you measure the decay rate, overall decay rate, all you've got is the summation of these A's. If you wanted to look at the individual ones, you have to look narrowly and just look at the rate of decay to a given transition. Now, I mentioned the radiative decay rate because you have to recognize that in many practical problems, there's collisions. And so there's also a rate equation for non-radiative decay. The rate of change of U, upper state, could be minus some sort of rate coefficient. That'd be the number over the radiative time. So the non-radiative time. So if there are collisions may be pulling it down much faster than radiation. So there's the radiative decay rate and the non-radiative decay rate. This number, the A's are independent of collisions, but this one depends upon the number density of the colliders and the collision frequency. When you have both of them acting together, you can observe a lifetime that's the inverse of the 1 over tau is the sum of the individual terms. So you have to be really careful. Are you measuring, you might want to know the radiative decay rate, but you're measuring the apparent decay rate. And it's a combination of these effects, and you have to be able to sort that out. Usually you do it by varying the pressure and extrapolating to 0 pressure. It's called a Stern-Volmer relationship. Okay, I just want to remind you that's in the notes. There's a lot of different forms to these line strengths. You have to be really careful about all the possibilities that you might use. We make heavy use of these units right here. Centimeters to the minus 2 per atmosphere. Sounds weird. Line strength per atmosphere. Why do we do it per atmosphere? I don't know, but it's in the infrared that's common. So all these things are related, but from P equals NKT, now you got to be careful about units again, because 1 atmosphere is 10 to the 6th dynes per square centimeter. So there's a 10 to the 6th floating around that you have to use. So S in my units of centimeters to minus 2 per atmosphere are some multiplier times, and there's a temperature dependence floating around. So you have to be really careful about these line strengths and the units that you have. Okay, Beer's law takes different forms. E to the minus k nu L in sigma L in terms of cross section, a lot of different forms. The sum of all these is dimensionless. There's no dimensions. Okay, what about temperature dependence? So we frequently use absorption in 2 lines to measure the temperature. How do we do that? We measure the absorption in lines with 2 different quantum states, and the relative absorption will be proportional to the relative populations, which depend on temperature. So what we care about is the relative line strengths. So you can, therefore, this general expression for the line strength compare it with, see how it varies with temperature, and you can take advantage of that to find a way to measure temperature. Okay, let's see. Band strength. Sometimes you hear the word band strength. Band strength is the sum of the line strength. So if we looked at an infrared band, the band strength is nothing more than the sum of the line strength. Because sometimes the band strength is tabulated. And you can, the reader or the notes will take you through this example of how you can get at the band strength of CO. So all this has to do with the fact that maybe you found a table for the band strength, but you want the line strength, so you have to be able to go back and forth. Or maybe you measured a line strength and you want to convert it to a band strength because that's what's in the literature. So you have to be able to go back and forth. It's just a question of units. Okay, and I'm partial to this system of CO because we spent some time on this a long time ago measuring this. The band strength of CO is known to about 1%, or better than 1% now. Oh, here's an interesting question. If I have the line strength or the band strength, I can calculate the Einstein A coefficient. Einstein A coefficient is the probability that a molecule in an excited state will spontaneously emit to a lower one. What do you think the average lifetime is for a molecule of CO in V equals 1? No collisions. What's the probability per second is going to go from 1 to 0? Remember, for sodium, it was something like 10 to the 8th per second. It only lives there for 16 nanoseconds or something. CO. 36 per second. That means the average lifetime is 28 milliseconds. And there are some transitions in the atmosphere that are important where the lifetime is really long. Forbidden transitions, they hardly ever happen, but they turn out to be important. So the A coefficient is a measure of the probability of emission, and it can vary all over the map. But remember, the absorption coefficient scales with A. A, small absorption. Big A, big absorption. So we've done quantitative line strengths, where you see the importance of the line shape. We're going to spend 1 hour or less going over line shapes. And then we'll have finished that part of the course. Any questions? Let's see, I started at, I guess I'm about roughly on time. Any questions? Yeah.
On slide 9, I think. No, slide 8.
8?
You had like the ratio of. Wait, you get there.
Should be able to do this. Here we go.
There you go. So the N2 over N1 is the ratio of the. Yeah. Why is there not another like exponential term for the G1?
For the G1, okay. I could have written N2 over N as G, e to the minus energy over Q. I could have written N1 as G1, e to the minus energy over Q. Take the ratio, the Q's go away.
Yep.
And the difference in the energies is H nu.
Oh.
This is nothing more than the ratio of the degeneracies and the ratio of the energy difference.
Okay.
H nu is the energy difference.
Okay.
Yeah. Okay. So he just was wondering where this came from here. This is the ratio of the populations in 2 and 1, statistical mechanics, where this ordinarily you'd write this as the difference in the energies. It's the difference between the energy of the upper state and the lower state, but that's just H nu. So this expression, then there's no Q in this expression because when you take the ratio of 2 states, it's not the ratio, it's not the fraction of all those molecules in that state, it's the ratio. There's just the ratio of the degeneracy. So I think probably got hung up on this. This is delta E.
Yeah.
Anything else? That's a simple one. Why don't you ask me a hard one? So there's a few important things here. You've been introduced, if you hadn't heard about it, there's something called the Einstein coefficients. He gets the credit. Fundamental thinking here, probabilities. And once the A coefficient is known, it's known forever for that transition, for that molecule. It's independent of temperature. It's just a probability of a molecule here doing something. So that's a new idea. And then you can relate that back to the absorption coefficient. And you can use that for emissivity, absorptivity. Everything boils down. You can tell me all the A coefficients. I'm done, except I'd have to know line shape. We derive the equation of radiative transfer. You can do that for emission, or you can do that for absorption. And we've seen that you actually do have to pay attention to line shapes. So we covered a lot of ground, and some of it may be familiar to you, maybe not. But and we also go to equilibrium to find relationships that still hold when you go away from equilibrium. So it's like a mind experiment. Imagine equilibrium. What has to hold? Microscopic processes are balanced. Now, when you go away, the individual rate coefficients don't care. The rate coefficients don't care. You may not have equilibrium, but the rate coefficients don't care. There was a question here somewhere. Yeah.
So a lot of these, either you could call them the Einstein coefficients or just the line strengths are tabulated, and your group has done a lot of measurements. So if you're just going to take one of these line strengths off a database like Nitran, how much should you trust these measurements?
Okay. So the database exists because of the atmospheric science community. So they're mostly infrared. So you'll say you're interested in water. Well, it turns out that there's 500,000 lines of water in the infrared. But you might use this database to say, I want to find the strongest line. Or maybe you're going to copy somebody else and you're going to say, I'm going to work on that line because it's been used before. The database will tell you the strength of the line in their units at some temperature. If you know the line strength for that transition at any temperature, you can calculate it at any other. So if the database is correct, you use the known relationships to get the line strength that you need at your temperature. You have to pay attention to this because the line strength depends on temperature. A coefficient doesn't, but the line strength has units. Okay, how good is the database? Well, in the areas where it's been heavily studied, it's a very good database. It's based on a combination of calculations and experiments. Where it lacks, but these are basically low temperature databases. They were developed for the atmosphere. As soon as you go to 2,000 degrees, there's some lines that are missing, and the database is poor. You have to check it. So these are mostly molecules. Now, for atoms, the situation is a little bit different, but there are databases. There are databases that give you the A coefficients or the oscillator strength. And so something's been heavily studied, it's really well known. Like I told you, the band strength for CO is known to better than 1%. But H2Os, but I know in my experience with Hitran over time, we found places where it was completely wrong. Lines were missing, partition functions were incorrectly specified, because they also give you the partition function. But gradually over time, it's just getting better and better, and there's a new version just came out in the last 2 weeks. That's the one you should be using. Yes?
How do you use the property of the gas, whether it's optically thin or optically thick?
Well, it's mostly just a way of thinking. If it's optically thick, no light's getting through, but it's emitting like crazy. So if you get it infinitely thick, it looks like a black body. If it's optically thin, you can expand the 1 minus e to the minus k nu L to be just k nu L. It's kind of like a mathematical simplification. So the real optically thin means weak absorption. So you don't necessarily want to be optically thin to do an experiment, but the math gets simpler. Monochromatic, you really don't care optically thick. You don't want it to be optically thick because no light comes out. You don't want it to be optically thin in the limit of no absorption because then no light gets absorbed. So, it's a unifying idea. People say, is it optically thick or optically thin? And you just kind of know where you are. Yeah.
I have two questions actually. First, this oscillation strength that you talked about, F1,
Mm-hmm.
you said it's a ratio. It's a ratio of what exactly?
It's the relative oscillator strength. It's the ratio of the oscillator strength to that for a free electron. So it's just a number. 0.3 I give for one example for sodium. It just means that absorption, that oscillator strength is a third of what it would be for a free electron, which is kind of like the upper limit. So it's just but I showed you for the infrared transitions, it's 10 to minus 5. Just a kind of a relative measure of how strong the absorption is.
Okay. And secondly, so you talked about the lifetime. For one, it was in the nanosecond order,
Mm-hmm.
and for the other one, recently, it was just like 3.
30 mil, yeah, yeah.
So with that being said, how does that parameter affect, like, does it make measurements easier since it stays there longer or something like that? Or
Well, remember, the lifetime is 1 over A. The absorption coefficient is proportional to A. So whereas for CO, which had the long lifetime, we might have to have tens of part per million meters to get absorption. With the sodium, one little bit of sodium in your flame and you see yellow. It's so sensitive. So high oscillator strength or high value of A means high activity per atom.
so it's relatively.
So the atoms, which are electronic transitions, tend to be much stronger absorbers or emitters. That's why you see, it's only parts per million in the flame that's causing the radiation that you see, the non-sooting radiation, whether it's blue or sodium. You put a little speck of salt on your burner and you see yellow. That's the sodium. Put your finger, just rub it across when it's off, you see sodium. So atoms are very strong. Molecules are weak, but we can still measure them because there's usually a lot of molecules. It's a measure, though, it's a measure of the strength of activity per atom. So we can live with the fact that the oscillator strengths are low for CO. They're big enough.
One quick question. So for example, you could have an emission from a single light, the electron first get excited, then emission to the triplet states. Is that possible in calculating this?
I think you're asking whether or not it's a metastable state. What's the strength?
Yeah.
Okay.
Yeah.
So that's kind of corresponds to a situation that's forbidden.
Right.
So forbidden is a funny thing. It's kind of like a parent's rules for their kid. It's like, this is the rule, but it's okay if you violate it a little bit. So it's like there's degrees of forbidden. So even though it's forbidden, it still happens. It's just very slow. So there's some transitions in the atmosphere that they might have a lifetime of seconds or hours. They still happen, but they're quote unquote forbidden. They're unlikely, and it's the result of metastable. It's a result of spin change. Molecules don't like to change spin.
But recently there are some experiments that you have started the emission from a single light to triplet, and then from triplet to the ground state.
They occur.
And
There's a difference. You've heard the words fluorescence and
right.
Phosphorescence. Fluorescence is for an allowed transition with a short lifetime, high probability.
Right.
Phosphorescence means it takes a long time to decay. What does long mean? Well, maybe it's a millisecond. Maybe it's a second. Maybe it's a day. So phosphorescence is the word that's given to these weak, quasi-forbidden transitions. They still happen. So just like when we had the vibrational transitions for a diatomic molecule, the probability of a delta V of 2 is 0 if it's a harmonic oscillator. But as soon as you recognize it's not exactly a harmonic oscillator, you start letting in some of the competition. It's some possibility. And there's different degrees of how perfect it is. So CO happens to be pretty harmonic. Some molecules are not so harmonic. So the relative strength of the allowed and the forbidden changes with how ideal the thing is. But it's nice to have these forbidden rules because it simplifies your mind. You can think, what's the dominant thing that's happening? Good. Any other questions? I've lost track of time. I think we probably should break and say, what's our schedule supposed to be? We're supposed to be through, I guess we're right on top. We're supposed to probably resume at 4:30, is that right? Resume at 4:30 and then finish by 5:30. Good. Okay, thanks.